this meeting. So I am going to record now. Okay, sorry about that. I forgot. So, okay, we're going to go into Gorilla Mux. This is a third-party library outside of Athens that Athens, of course, uses. So I'm going to go to the GitHub webpage for Gorilla Mux. So Gorilla Mux at its core is an HTTP router. So you can basically set up an HTTP server, and you can then say, at this path, I want to handle a GET request, and I want to execute this code when that request comes in. So if we go down here to examples, Athens does this call, mux.newRouter. And then in the add proxy routes code that we'll see in a second, we call these handle func methods. So heading back into Athens, here's that simple new router. But then we have this r.use request logger. So going back into here, there's really no r.use anywhere in here. Actually, let's see if they do have it in here somewhere. I'm going to do a search for .use. So yeah, here we go. So we've got a thing called middleware. So middleware, if you're not familiar with it, just really briefly, middleware is code that automatically gets called before or after any of the routes get called. Any of the code that handles any of those routes get called. So I'm going to show you what our middleware looks like. So we've got this mw.request-logger middleware. So heading up to the MW package, I'm going to go to our imports and show off where that package actually is. So scrolling up to our imports, we've got this MW package inside of Athens under pkg/middleware. So I'm going to head into there. We can see what a middleware looks like. So we've got our pkg/middleware, and going back down here in our r.use, we've got our log entry middleware. So that is under here. And we've got our log entry middleware here, and we passed a logger to it, and that's going to be a topic for another office hours, because that's actually a pretty big topic. And this thing returns a mux.middleware func. And so we actually don't need to go into the Gorilla Mux documentation to figure out what this thing is, because we actually return one right here. So this is a function that gets called, and it returns another function. And we do that because this returned function needs to use the logger that we passed in. So this is kind of a functional programming concept, because we're calling a function and it's returning another function. And that other function does this thing called a closure. So it uses this parameter that got passed in. So this, if you see this anywhere, it's a really powerful concept. And if you want to Google it, you can just Google Golang function closures or just function closures, and there will be a ton of documentation about how this works. So this function that we return itself takes in an HTTP handler. And then it itself returns an HTTP handler. And this is another function. So we are returning a function, and inside of that function is another function. So this is a 3 levels of functions deep, okay? So the kind of objective of middleware is that we want to take a handler in, and then we want to do some stuff either before or after the actual handler to be executed, and that's the code that responds to whatever path is being called. So in this case, since this is a log entry middleware, we want to do some logging, okay? So right in here, we have this F, and this F is basically an HTTP handler. So if you've done HTTP servers in Go, this will be pretty familiar. And if not, we can go check out the documentation for that. So this is in the standard library, and I'm going to go to type handler. And we can check out here. This is basically what a handler looks like. So any code can implement this handler struct. And what we're doing here is using this handler func. So going back to the documentation, handler func is basically the way that you can make a handler just by writing a function. So this function takes in this response writer and also takes in a request. So this is an HTTP interface. This response writer is an HTTP interface that you can send HTTP responses to. And then this pointer to a request is basically information that comes in from the HTTP client. So we're a bunch of levels deep. And going back to the code, essentially we're writing a new handler. And this handler does a bunch of logging stuff. And then it calls the actual code to be executed by it calls the actual code that gets executed as a response to whatever route is being called. So if it's a GET request to, /info, I'm just making that up out of thin air. This stuff will be executed. So we're setting some context for the logging that this handler will do. And that will always get executed no matter what request comes in. So if this is a GET request for /info, this stuff will be filled in. So this will be a GET, and this will be /info, and this will be the full URL that's requested. We're going to set up some logging context, and then we're going to call the actual code that should be executed in response to the GET request to the /info. Okay, so I went pretty deep into middlewares. Going back to app.go, we actually have a couple of middlewares in here. We've got our middleware for logging. We've got some middleware to take care of HTTPS, so secure endpoints. And then we've got another middleware to set up, to determine and set up the HTTP content type. So this is another one of ours. I'm not going to go into it right now, but you can certainly check it out. And it does a lot of interesting and important stuff to make sure that the HTTP content type header is set to the right thing so that the Go CLI can handle, can send the right requests and handle the right responses. Okay, so going down here, we have our first .handle func call. Okay, so this is a .handle func for the root route. And what this essentially is doing is we're making sure that certain front ends, so certain load balancers that might sit in front of Athens, or certain systems that might do a health check to make sure that Athens is still running properly. They might make a GET request to this just root URL. And we want to make sure that we have a handler that can accommodate that GET request and send back some kind of empty-ish basic HTTP response, so that whatever is calling this thing can know, okay, Athens is still up and it's still doing something important, and we don't have to try and restart it or start up another one. So heading over to this health handler, I'm going to go into here. And this is the super, super basic way that we tell systems that make a health check to us that we're okay. So just your basic HTTP handler func that we just saw. And we're using the HTTP response writer here to basically just write back an OK HTTP 200 response. So this might be the very simplest handler you'll ever see. But in this case, it's actually important because let's say you're running Athens behind like a Google Cloud load balancer, or an Athens or Azure load balancer, or AWS, and you've configured one of those load balancers to check out if Athens is running on maybe a backend. And if it's not running, then maybe the load balancer would say 404 to the Go client. And this is the way that we can tell the load balancer how to ask Athens if it's healthy and running. Same thing as if you're in Kubernetes, where Kubernetes can do those similar kinds of health checks. Okay, so that is our first handler. This is a GET request to the / to the health check. Okay, so we're gonna go down here. Here's some observability stuff, and we're gonna get into that. That's a huge topic, and we'll get into that in a future office hours. More observability stuff. We checked out some of this configuration stuff before. And now we've got our big one, our proxy router. So we're setting a proxy router variable to the exact same thing as our R. So scrolling back up, remember that R is that very, very, very first mux.new router. Okay, so heading back down, we've now got our proxy router set up. And here we go. Now we're actually going to go into this big meaty function called add proxy routes. So add proxy routes takes in that pointer to the router that we created in the app.go that we just saw. Before, in I think our first office hours and our last week's office hours, we saw how the storage.backend is created. And we also saw in the very first office hours how the config is created. And then I mentioned, sort of really briefly, I mentioned the logger. That's being passed in as well. And so, like I said, we will go into logger later, but basically in almost all of the Athens code you'll see, loggers will be used. So it's important to at least notice them if you're making Athens contributions. Because they're really important. It's good to have, you know, an Athens server log out to tell you what it's doing. And so if you're adding code, make sure to use it. And if you don't have access to a logger in your code, you can copy from somewhere else that does get access to it. Or if it doesn't make sense, you can submit the PR without it, and we'll guide you through, you know, how to get access to a logger and how to use it too, if you need help with that. So on to the additional .handle functions. Okay, so I'm gonna head down to the, let's go down into some of the meat of it. Keep going down. And we're gonna go into the .register handlers function. And I kind of called this the meat of it because register handlers is actually what creates the routes for the actual module download API. Okay, so there's plenty of other stuff above this that's important too. But I really want to start by focusing here because this is the module download API, and that's kind of, like I said, the whole point of Athens. So register handlers, I'm going to search for that. And if we check out here under pkg/download/handler.go, register handlers takes in the same exact mux.router that we created up in our app.go. So we're now 2 levels deep from app.go. And then it takes in some specific options just for the module download API handlers. Okay. So the first thing we're doing here before we call any more .handle functions is we're creating yet another cache control middleware. So this middleware is going to make sure that before any of the handlers in this function return to the Go client, we're making sure that we tell the Go client that there should be no caching. And that kind of makes sense because we want things like the /list and /latest handlers to never be cached because the list of versions and the latest version could always be changing. We don't know when it will change, and we don't even know why it would change either. So we're just telling the client, never store this in your cache. and always check again with Athens to see if something got updated. Okay. So now we are creating our first handler for list. So heading up to path list, where did that go? Do a search for that. So path list is a constant here. And basically path list is a path that GorillaMux understands. And it uses this kind of regex format. And this is saying that we want a slash and then we want whatever is here before the @v to be captured as this path variable that we're going to call module. And then there's this constant string after the module that is @v/list. Okay. So we are going to go back one to our path list. And this is a new concept here for GorillaMux. So remember that a middleware can take in an HTTP handler and then can return another HTTP handler afterward. Okay, so that's exactly what Nocache MW is doing. It's taking in our list handler and it's returning another handler that makes sure that the list handler gets called, and before any response actually gets sent over the network to the Go client, that response has a Nocache in its cache control headers. Okay, so checking out the list handler in here, we'll get into what this download protocol thing is in a second. Actually, we might wait a little bit to get into that. We've got a log entry, so that is sort of the basis from which we start doing our logging. And we've got this download file, which again, we're going to have to wait a little bit to get into. Okay, so our first step in our handler that we're going to return from this list handler function is we're going to use this paths.getModule function to figure out what the module actually is from the path. So that's where this thing comes in. So this is actually going to extract the module name from the path that came in from the HTTP request. So we're going to check out this function. It's actually not super complicated, but since it's used, like, I think it's used in almost every one of our handlers, it's a really important one to at least know that it exists. So here we go. We've got our get module. It takes in our request because that's where the module needs to, that's where the function needs to extract that module path variable from. And then we've got this function called mux.vars. Okay, so mux.vars is built into GorillaMux. And it is the way that you can extract all of the path variables that are listed in the path we pass to GorillaMux. And it returns them all as a Go dictionary, a Go map, I should call it. I was working in JavaScript just before this, so I get map and dictionary and it's jumbled in my head. So a Go map, and we want the module path parameter from that map, and we want it, we basically just use the bracket syntax to get the value for the module. And then of course, if we didn't get a module back, we're going to just return an error saying, well, whoever called us didn't put the right URL format, there was no module in it, so we're going to return no module. Okay. And we could also have done something like this, just as a note. And we could have done our return that and blah, blah, blah. Essentially, they're the same thing because we know that it will be an empty string if there's no module. But that's just a note. So if you're using Go maps and you see this syntax in the future and you're not familiar with it, that's what this is. But for us, we're going to just check an empty string and we're going to return our error. But if we are not seeing that empty string, that means there was at least something in that module path parameter. And we're going to figure out whether or not it is an actual valid module. So I'm going to go into there. And decode path takes in that module path parameter value. And then it itself calls decode string. So let's go check out what that is. And going down here, this code is actually code that we pulled out of the core Go modules code in the Golang repository. And this does a lot of things. So the most important thing that it does is it figures out whether or not there are capital letters in the module path. So if you're familiar with sort of like the history of Go dependencies, Go dependencies didn't distinguish between modules, and at the time they were called packages. It didn't distinguish between package names that had capital letters and lowercase letters. So what that led to was on some systems that had case-sensitive file systems, if there were two different package paths, then they would be unique on disk, because there would be one that's like uppercase whatever and one that was lowercase whatever. But if they were case-insensitive module paths or package paths, one would overwrite the other. And that led to all kinds of craziness that no one liked, and it was confusing. And we wanted to fix that with the module system. So we use exclamation points in the module system. So right before a letter, whether it's in the module path, whether it's uppercase or lowercase, we make sure that it's always lowercase if it was uppercase. And also if it was uppercase, we put an exclamation mark before the letter. So I'm just going to write an example here, if I can type properly. I'm going to make up a module path. So it would show up like this in GitHub. But in the module system, it would show up like this. Okay, so we've got to figure out how are we going to actually store this thing in our storage backend. So in our storage backend, since that thing is always going to be case sensitive, it's going to be stored in MongoDB or AWS or Minio or GCP or whatever it might be. We're assuming that our storage backends are always case sensitive, which may be a big assumption, but for now, all of our implementations have been case sensitive. So we want to store it like this, but since we're getting it in like this, we're going to try to do that conversion. Okay, so that's not the only thing that decode string does, but it's a large part of what decode string does. So I thought I'd point that out. Okay, so going back here, our decode path pretty much just calls decode string and then returns the path. Going back one more, our get module is the thing that's grabbing the module out of the path parameters that Gorilla and Mux gave us, and then it's calling decode path. And if you notice, we're kind of propagating these errors back up. So if we go one more level up, we're back to our list handler. So we got our get module, which calls decode path and calls the decode thing and calls all these decode functions everywhere. And now we're back up into our HTTP handler. We're checking that error. That's the error that got propagated all the way back up. And if we got an error, then we're going to do our logging, and we're going to just write back an internal server error. So this may not be, now that I'm looking at this, this might not be the perfect HTTP error to return. If someone has a better idea for a better HTTP error, speak up or submit a PR or an issue. That would actually be great to have a discussion about. But for now, this is at least what we got. So this is that way to write a header back to the Go client. And then we're just returning. So in Go, for HTTP handlers, we don't return the header call. So this write header call on the http.response writer, it actually returns nothing. So what we do is we write the header down, and after we return, the HTTP server library will then know to immediately write all of the stuff that we've set on the response writer. It'll flush it all down into the client, the Go client library. So that's an important one to remember. It at least trips me up a lot when I forget to return. Then I continue on after I set all my error stuff up, and I actually didn't return an error thing back to the client. Okay. So now we're going on to the more exciting stuff. Okay. So we're going to go a little bit outside of the pure HTTP handler stuff because the rest of this is kind of familiar. So we're doing this dp.list function, and I'm going to dive into that in just a second. But then we're doing more error handling, and this looks a whole lot like this error handling. And then we're printing out this thing called versions by joining versions with new lines. So versions is a string slice of all the versions for the module that was asked for. And we're just printing out that list as just a bunch of versions in a new line separated list. And then finally, at the end of all this, we're returning a handler func that basically is just all of this. So we could have actually easily just done, if I'm going to comment all of this out in a second, copy that. We could have actually easily have done this. But we decided to make it a little bit cleaner and to declare the actual handler func in a separate variable and then return http.handlerfunc with just that variable. It just kind of cuts down on the number of parentheses you have to write, but really there's no other reason for it. So let me uncomment everything. And let's head over to the download protocol so we can check out what this list function does. So I'm going to head over to protocol.go. So this is in pkg/download/protocol.go. And check out this type protocol. This is a protocol interface. So we talked about interfaces in the storage system. Protocol is an interface for handling how do we do module list and module metadata and actual module source code. So this is a kind of wrapper around the storage interface and a couple other interfaces. So that's things like managing how we access storage and other stuff like that. And these functions actually map to specific module download APIs. And they're actually listed in the comments. So we're going to look at list, but the handlers for a lot of the other core HTTP handlers look a lot like what we just saw in list, except they just call different functions. So we've got the metadata for information on a module. We've got the latest version of a module, the metadata for the .mod file of that module, and then finally the actual source code download function for the zip file. So let's check out list, what list looks like in an actual download protocol implementation. Sorry, I've been talking a lot today, so I've got my brain all scrambled. So here's the kind of constructor for a new protocol. There's currently only one implementation of a protocol. And this implementation basically uses the Go CLI behind the scenes to implement all of these functionality. Go list, go info, go mod latest, go mod get, and then go mod download. So this constructor returns a lowercase protocol, that's this struct. And then headed down here, you can see there's this download file mode, which has to do with filtering, and that's a whole nother office hours. We've got our storage backend, which we've checked out before. We've got this thing called a stasher, which manages a bunch of different Athens to make sure that they don't all flood the storage backend at once. And then we've got this upstream lister, and we're going to check that out in just a second. Okay. So heading down to list, here's our implementation of it. We've got a couple things here going on. Okay. So again, this thing is called when anyone does that go mod list call. That gets sent up to Athens, and that generates that whole thing where we do a get slash the module name slash @v and then slash list. So basically, this is exactly what happens when that call comes up to Athens. Okay. So again, we've got some logging stuff going on. And then here's the interesting stuff. Okay. So first things first, we're setting up these two lists, actually, these two string slices. So essentially what this function is going to do is it's going to use let me head back up here. It's going to use this upstream lister to try to get a list of modules. But at the same time, it's also going to use the storage to try to get a list of modules as well. So we do this to try to get the most up-to-date list of module versions for that specific module. But we also try to make sure this thing is as resilient as possible. So this lister actually goes up to the upstream. So that might be the version control system, or it might be an upstream Athens, or it might be like proxy.golang.org, or any one of the supported upstreams that Athens has. But of course, Athens has to talk over the internet to get that stuff. So it might have to talk to GitHub, for example, or proxy.golang.org. And GitHub could be flaky, or proxy.golang.org could be somehow not accessible for whatever reason. Or maybe you're running inside a firewall and Athens doesn't have permission to go upstream. In any one of those cases, this thing is going to return an error. But we assume that Athens kind of always has access to its own storage backend. So that's why we call this. So we pretty much know that p.storage.list is going to return an actual list of strings, unless something is really wrong. In that case, of course, we're going to get an error. But at the same time, we also know that p.storage.list might not always have the most up-to-date list of versions. So it's kind of like this is a fallback. Hopefully that kind of makes sense. There's a ton of documentation about why we do this and how this stuff works. But the first step here is basically to make sure that in storage we actually have the module and we have some list of that module's versions. And it kind of explains here that at least we want to make sure that there is at least one version of this module already stored in storage. And then in this case, we want to see that some upstream is actually there. So if we can talk to GitHub, we want to make sure that the actual module is there in order to get that list. And then just going down a little bit more, there's a lot more sort of formatting we take care of. But down here, we call this function called union. And union is that place where we put together the list of modules that we had in storage and the list of modules that we got from GitHub or wherever the upstream is for Athens. And union is kind of what you think it is. Let me figure out where union is. Union basically takes both of the VCS string list and the upstream and the storage string list, and just puts them together. But it makes sure that it doesn't put duplicates. So it's kind of like a set union to make sure that everything is unique. And we assume that since we're going from top to bottom, we assume that the upstream list and the storage list are both sorted. So if we're going top to bottom, we essentially are making sure that the result is also sorted. It's not a requirement, so this is not necessarily going to be sorted, but as an implementation detail, usually it is a sorted list of versions. So that's kind of nice to see that in the output of Athens. So heading back, we are in our list function, and we kind of manage these two concurrent calls with a wait group. So how do people feel about wait groups in Go? Up, down. We got one up. Okay, let me explain wait groups a little bit so we're all kind of on the same page. So a wait group is built in to the Go synchronization and concurrency libraries. Okay, so I'm going to go actually check out the documentation for wait groups so we can see some sort of basic examples. And then I'll come back into this code and sort of apply those examples to what we're actually doing here. So you can find this documentation in godoc.org, and it's under /sync. So sync has a bunch of different stuff. Really the cool stuff, to me at least, in my opinion, is wait group. But you can do things like locking and synchronizations and synchronizing maps and condition variables and all sorts of stuff under the sun. But really, I actually think wait group is cool because it doesn't make you look at all these lower level details. Really, you can just say, I want 5 different things to happen at once, and I want to make sure that I don't continue on with my code until they're all done. So what that essentially means is you can launch 5 Go routines, and then after they're all launched, you can wait at some point until they're all done. Whether or not they had errors or they succeeded or whatever, you can just put this line in the sand and say, I'm going to wait here until all of the ones that I just launched are done. So we can check out their example. Basically, they are trying to fetch 3 different URLs in 3 different Go routines. And they're just saying, create the wait group here. This is the standard way to create a wait group. Add 1 for each URL. So add 1 to the wait group. And that means that we're adding, when we add 1, we're telling the wait group, there's 1 more Go routine to wait for. So after this for loop is done, we have told the wait group, I want you to wait for 3 Go routines to be done. And then the second to last piece to wait groups is calling wg.done. So basically what that means is we're telling the wait group, okay, I'm done, so decrement that counter. So once we've done our wg add for all 3 URLs, there will be 3 Go routines running. And when each of them are done, they will decrement that wg.add call. And then at the very end, wg.wait just waits until the counter reaches 0. Okay. And this is really the important thing to me, at least, is this is the place where we draw that line in the sand and we say, okay, I'm going to wait until all 3 of those URLs have been downloaded. Once they've been downloaded, then I can continue on and do my thing. So this is a pretty simple example. Let's go apply that then to our code. So what we're doing is we're trying to download the list of versions from our storage and from the upstream. So that's 2 things going on at once. So we do our wg.add 2. And then in each of the launched Go routines, here and here, we are deferring the call to wg.done, here and here. So we're not doing it in a for loop because we know there's always going to be only 2 things that should happen. Okay. So now check this out. We are setting stir list and sair equal to our storage call. And then we're setting our go list and go air equal to our call to the upstream lister. Okay. But after we've launched the 2 Go routines, we have no idea whether or not either is done, which means we have no idea whether these 2 variables or these 2 variables have been set. So we can't do anything until we know that both of these Go routines are done. And of course, that's why we call this. This is that line in the sand. So after this point on line 91, we know that these two variables and these two variables have actually been set. And that's why we start doing these checks here. We check the storage error and we check the lister error and all these other good errors that we're checking. We use that wait group to know that they've been set, that both of these calls to storage and the upstream lister have completed, and at least they've returned something. But of course, we don't know if they've returned an error or whatever, but we know that they've at least returned something. Okay. So I've talked a lot. We have 12 minutes left. So I'm going to pause and let's see if anyone has questions or if we've got some thumbs to indicate if this is making sense, sort of, or I should back up. Okay. Got one of these. Okay. Cool. All right. So there's plenty more stuff in here. We made sure that this is super well commented or decently commented. So hopefully if you're jumping into this code, these comments might not make a ton of sense because they're super specific to sort of deep issues that might come up with Go modules and parsing out module versions lists and stuff like that. But if you read these and something doesn't make sense, we hope at least that this will be a good place to start asking questions. And that would be instead of seeing something like this. Like if this was completely gone, it's like, well, what is this? Why are we checking these errors? And what is not, or is repo not found error and stuff like that. So if you do jump into this code, read the comments just briefly. And if you still have questions, just jump into Slack or file an issue or whatever makes you most comfortable. You can always DM me too. And just say, you know, I read these comments. What does this actually mean? I don't get what they mean by, you know, we'll get different results because GitHub is up again or whatever it may be. And either I will answer the question or I will point you to the right person to answer the question. Or I will figure out something. I will wave my magic wand and figure out a way to help you. Okay, so that was list. So I'm going to super briefly go back up the stack, back to that add proxy routes to sort of get our bearings, sort of where we've gone in our journey from the route handler all the way down to the depths of Athens. So going back, we were back in here. So this was our add proxy routes. We went down into here, download.register handlers. And download.register handlers, I believe that was under here. We had our list, our latest, then we've got our three sort of core download API functions. And these are the ones that give you the info metadata, the go.mod metadata, and then actually the source code. But one thing that I really want to point out here is that the list and the latest endpoints, they use that no cache middleware. And that's because, like I was saying before, we don't know when the list of versions might change. We don't know when the latest version might change. So we want to make sure that's never cached. But these ones that have the metadata and source code for the modules, we really want to make sure those never change. That's part of the big point of Athens, is to make sure that your dependencies never disappear out from under you. So we never say no cache. We want to make sure that every HTTP server in the chain between Athens down to the Go client, and we also want to make sure the Go client itself cache this stuff forever. And that's really important, and it also makes things a lot faster. So I'll give you an example of how this stuff can be a lot faster. So have folks seen this athens.azurefd.net thing that I've been playing around with? If you haven't, that's cool. This is basically, I deployed in Athens to the cloud, and I tried to deploy it with cool technology that I wanted to play with. But basically what this is this one Docker container of Athens running in some region in the US that I can't remember. But what I did was I put it behind this caching proxy. So whenever go-get or go-mod-download or go-list makes a request to this URL, it's actually making a request to a CDN, a content delivery network. And that CDN then will check its cache. And if the module is not in its cache, it will go and do the request back up to Athens, get the response back down, return it out to the Go client, but also it will cache it globally. And it will cache it only if there are none of these headers. So in the case of list and latest, it will never cache that HTTP result. But in these cases, it will always cache them forever. And that's really handy because it will cache them globally. So the next time I do a go get or a go list or a go mod download or whatever, I'll be fetching that big, huge zip of source code or these metadata pieces from a location that's super close to me. And that can be super handy because, like in this case, for a source file, we can be talking about 9, 10, up to like 25 megabytes. That makes a huge difference if I'm downloading it over Wi-Fi from Starbucks, whether I'm downloading it from down the street versus I'm downloading it from some Athens that's running, across the country or on a different continent or whatever it may be. So that's important. But also another piece that's important is that Go modules, the Go module system keeps a on-disk cache on your machine of all the different versions of all the different modules you keep. So it itself will store this stuff on your machine, on your disk, according to those cache headers as well. So that's an important piece too, make sure that Athens plays nicely with the Go CLI as well. Okay. So we talked about sort of how the HTTP handling works. We talked about the implementation of one of the core Go module API handlers in Athens. And then we just talked a little bit about the middlewares and the caching stuff. So I'm going to leave it at that because I feel like that's a lot. But next week, I think we should continue, if you all are okay with it, I think we should continue talking about these handlers because they're kind of the top level and they go down and touch all different pieces of the code in Athens. So are people okay with that? Medium, down? Cool. All right. So let's do this at the same time next week. So that would be Tuesday, starting at 2 p.m. Pacific time. That's my time. And I will put this up on our calendar and it will have the time in your time zone, just so we're all, on the same page. Cool. Before we head out, do we have questions, comments? Okay. So remember, you can always DM me. I know we've got a few contributions that started from these office hours, so I'm super happy. Thank you for doing that. Yeah, and if you want to make contributions or you have questions, feel free to DM me, or if you're comfortable, you can ask in the Athens channel too. All right, everybody. You're welcome, James. Hope to see you all next week. Take care.